We're going to look at graphing exponential decay functions in this tutorial. Just like with exponential growth, our form is still going to end up being y equals a times b to the x, with x as my exponent. The same as last time, a has got to be greater than 1, or greater than 0, excuse me. But this is the difference. I've got that underlined in blue. 0 is less than b, which is less than 1. So that means that my b value is going to be between 1 and 0. It's going to be a fraction. So, and that's here again, b is my growth factor, and that's what's going to tell me exactly how much it grows by, or how much it shrinks by. In this case, we're going to be shrinking. I have an example, y equals 1/2 raised to the x. My suggestion to start with, we want to make a table of values and just look what happens to x and y. I like to pick numbers all the way around 0, so let's start with -2. We use -1, 0, 1, and 2. So we're going to basically just plug these x's into this x, and we'll just work those out. And the first one's pretty straightforward. We have 1/2 to the -2 power. Well, remember, that's like flipping, so we don't want it to have a negative exponent. So we're going to flip that over and change the power to 2. Well, that's pretty easy. That's just 4. Okay, keep on going. 1/2 to the -1. Well, that's even easier. That's just going to be 2. And then 1/2 to the 0 power is even easier. That's just 1. And of course 1/2 to the first power, well, I hope that's pretty straightforward. That's just 1/2. And then 1/2 squared is 1/4. So we're going to take all that and we're going to go ahead and we're going to graph it. So let me erase my work here to put my graph down. We're going to go ahead and we're going to graph the x's and the y's. Because we know what the exponential functions look like, I've really already got a rough idea of what this is going to look like. It's going to look similar to what we had earlier, but it's going to have it's going to go a different direction. Instead of going up to the right, it's going to go down to the right. So let me label the parts. This will be 1, -1, -2. This will be 1 and 2. So we'll go up to, let's see, 1, 2, 3, 4. So we have -2, 4. Let me try that again. We have -1 and 2. Why does it do that? Seriously? There we go. And then we have 0, 1, which is one common point. All of your parent functions are going to share that point 0, 1. We go to 1, we have 1/2. If I can actually draw a dot. And then 2, 1/4, which I probably won't be able to get real close on. But you get the idea. It goes kind of in this direction. And this is my exponential decay. In fact, my growth factor in this case is 1/2. So it's shrinking by 1/2 every time. And you can look at it. It goes from 4 to 2 to 1. Half of 1 is 1/2, and half of 1/2 is 1/4, and it's going to keep on going. And that's what this particular function does. It cuts my y values in half every time I plug in another x. And so this is a basic function for growth and decay. Our next example is going to be y equals -3 times 2/5 to the x. Now notice you have a couple of changes. You have negative and you have a number outside the fraction, outside your growth factor. So we're going to have to take that and create a couple of points before we can graph it. Alright, here we go. We're gonna make a couple of XY points. Just a couple, because I already know the shape. I actually know that this is going to be turned upside down because of my negative sign. So if we plot a couple of points. That's easy one, right? Plug 0 into x and make sure your fraction become 1, and 1 times negative 3 is negative 3. Plug in positive 1, and you're going to get negative 3 over 1 times your fraction of 2/5. And that's easy to see that you get negative 6/5. And so that gives me this fraction. And I know that it's a fraction, but it's not really that big a deal because I'm going to plot it. I'm going to get close. So I'm going to plot a couple of points here. If we plot my first one, it'll be there. The next one, it's more than negative 1, but just a little bit more than negative 1. So we're just going to put that point right there, and we're going to go ahead and draw it in and put our arrows on the end of it. One thing to note, just like with exponential growth functions, you have your horizontal asymptote. If there is no vertical shift, there is no change, then that means that your horizontal asymptote is still y equals 0. Okay, it's going to be y equals 0 all the time. Okay, if we have one that changes, if you had something that said, maybe we had what we had now, but at the end of it it's got plus 3 or something like that, then you would have some things to change. But we'll see. Okay, so this is your graph. I got this by just plotting 2 points and knowing what the function looks like to start with, also knowing its horizontal asymptote. The next example is y equals 3 times 1/2 raised to the x plus 1 minus 2. So here we have a lot of the changes taking place all at the same time. So a couple of things that can make this easier. The parent graph is y equals just 3 times 1/2 to the x. So if I wanted to talk about how has this changed, I can say that it's gone to the left 1 and down 2. So however you want to do this, I'm going to give you what I think is probably the most direct approach, simpler approach. So if I were to plot, let's plot a couple of points just from my parent graph. So if I take those points, I can just move them left 1 and down 2 and then redraw my dots and I'm good to go. And so the easy one, of course, is always 0. 0 would be 3, and I can plug in, let's say, the point 1. That would be 3/2. Okay, so this would be x and y. If I were to make a new xy chart, call this the new one, I want to graph this. Basically, I want to shift them left 1 and down 2. If I take each of them, let's look at the x coordinates for a minute. So from the x's, we're going to take them and we're all going to subtract 1 from them. So that's going to give me negative 1 and then of course 0. I'm going to take the y coordinates and I'm going to subtract 2 from them. So we have 3 minus 2 would be 1, and 3/2 minus 2, that's 1.5, so that would give me negative 1/2. Alright, so I'm just going to go ahead and graph those points with one other thing that I have to be very careful about. That is going to tell me my horizontal asymptote. So I'm going to go ahead and draw that in. Horizontal asymptote right at negative 2. This graph will not cross that line. If it does, then you've made a mistake. So I'm going to go ahead and plot my new points. I'm going to go ahead and plot the points right here. So negative 1, 0. Or I'm sorry, negative 1, 1. So here's negative 1. Go up to 1. So there's my point there. And we're going to plot the point 0, 1/2. That's going to be right about in here somewhere. And I can already see my graph beginning to take shape. Come down through here, and it approaches my graph, my horizontal asymptote like that. I graphed that complicated object by number one, knowing the shape to begin with. Number two, I knew my horizontal asymptote because it's always the vertical shift. Number three, I knew the parent function, and I just basically shifted my points according to what they needed to be shifted, according to the equation. The domain and range. The domain, this is a real easy problem. Domain, it's going to be all real numbers. Exponential functions, almost, I want to say they're always all real numbers. So we'll say almost always because I'm not 100% sure. My range, this is actually quite easy. I need to find my horizontal asymptote, which is at -2. This graph exists above that number, so that's going to simply be y is greater than -2. Not equal to, because the graph never touches it. So if I wrote that in interval notation, it would be -2, comma, positive infinity. Both getting parentheses. And that would be finding the domain and the range of those situations. In the next example, I've given you 3 equations at the top and 3 graphs, and we have to kind of match the equation to the graph. First thing I notice is that each one of them has a different asymptote. And so I have to be careful. Well, 2 of them have the same asymptote, but one of them is different. So I'm looking for one that has a vertical shift. So let's take A, for example. A, I can tell it right here at 4, it has a vertical shift up 4 because the horizontal asymptote is at 4. If I go up and look at my equations, I can see that only one has a vertical shift of 4. So this is going to end up being A. The next part, I'll look at these and I can look at the differences. Well, this is going to be decay. This is growth. So look at my equations of the 2 left. This is decay, so that's going to get B. And this one is exponential growth, so this is going to get letter C. When you're looking at equations, there are certain key elements that kind of set them apart. The first thing you want to look for is your vertical or your horizontal asymptote. That's probably the easiest thing to identify. The next thing would be to look at the initial point. The initial points here, if I can, I'll highlight them for you. What we have here, we have an initial point of 0, 5. What we're looking for is the Y-intercept, 0, 4, and 0, 4. So I could have plugged in 0 for x and just see what happens, because that's pretty easy in all of your equations. If I can plug in 0, the exponent really kind of goes away, and it's left with whatever's left over. And so you can see that that's another easy part. The third thing we can look at is if it's growth or decay. And those things will most definitely be different, if it's growing down to the right or if it's going up to the right. Those are big differences. So when you're looking at graphs and you're trying to say which graph goes with which equation, make sure you check out the Y-intercept, you check out the horizontal asymptote, and you check out if it's growth or decay. Those are some great tips in order to graph things, or if I've given you an equation and it's kind of a multiple choice scenario, or if you're simply trying to match up things kind of like this example is, it makes it a lot easier. And that is graphing with exponential decay functions.